Good morning, colleagues and fellow surveyors. Today, we are diving into one of the most critical aspects of geodetic measurement, which is the concept of error, propagation, and how it dictates the reliability of our spatial data. In our field, we must accept that no measurement is absolutely perfect, as every distance we tape, every angle we turn, and every satellite signal we receive contains some inherent uncertainty. The true challenge of surveying is not just taking measurements, but understanding exactly how these tiny, inevitable imperfections travel through our mathematical formulas and impact our final coordinates. To understand this journey of uncertainty, we must first look at the core mathematical definition of error propagation. When we are out in the field, we rarely measure our final desired values directly, but instead collect raw variables like distances and angles to compute downstream values such as positions. Error propagation is the statistical principle that dictates how the random errors in those independent field observations accumulate and transmit through our geometric calculations. If we do not account for this, a series of minor acceptable errors at the beginning of a traverse can quietly multiply into a catastrophic misclosure by the time we reach our final control point. A perfect playground to observe this phenomenon is the standard traverse computation, specifically looking at how our field measurements determine latitude and departure. In coordinate geometry, latitude represents our northings, calculated by multiplying the measured distance by the cosine of the bearing, while departure represents our eastings, found by multiplying that same distance by the sine of the bearing. Because both of these fundamental coordinate components rely on the exact same two field inputs, any single mistake made while setting up the total station or reading the prism will instantly bleed into both calculated directions, but it will do so in very different ways depending on our orientation. Let us look closely at a scenario where our survey line runs nearly due north or due south, meaning our bearing angle is very close to 0 or 180 degrees. In this geometric setup, the cosine of the angle is at its maximum value of 1, which means your calculated latitude becomes extremely sensitive to any errors made in your distance measurement. If your EDM or tape is miscalibrated by 2 centimeters, that error will translate almost entirely into a 2 centimeter mistake in your northings, while your departure remains largely unaffected by the distance error, because the sine of the angle is near 0. However, this north-south orientation creates the exact opposite effect when we look at our bearing errors and how they impact our departure. Because we are traveling in a straight vertical line on our grid, any slight angular deviation or swing in our bearing acts like a long lever arm, swinging our estimated point sharply to the left or to the right. This means that for a north-south shot, a minor error in your angular alignment will barely change your latitude, but it will severely compromise the accuracy of your departure, pushing your calculated coordinate off to the east or west. The script flips entirely when we change our direction and analyze a survey line that runs almost due east or due west, where our bearing is close to 90 or 270 degrees. Now, because the sine of the angle approaches 1, it is our departure that becomes hypersensitive to any distance measurement errors, absorbing the brunt of our fieldwork imperfections. Simultaneously, the cosine drops to 0, making our latitude highly insensitive to distance errors, but extraordinarily vulnerable to any angular errors that swing our alignment north or south of our intended path. To mathematically manage these overlapping vulnerabilities, geodetic surveyors rely on the variance-covariance propagation law, which uses partial derivatives to calculate the total statistical error. This law gives us rigorous formulas showing that the total variance in latitude is the sum of the squared distance error scaled by the cosine plus the squared angular error scaled by the distance and the sine. The departure variance is calculated using the inverse combination of those same trigonometric weights, giving us a precise, quantifiable look at our total spatial uncertainty. The most vital takeaway from these propagation formulas is the presence of the distance variable multiplied directly by the angular error. This mathematical relationship proves that as your sight line or shot distance grows longer, the destructive power of your angular error increases exponentially. A tiny angular error of just 5 arcseconds might be negligible on a short 50-meter shot, but if you extend that same shot to 5 kilometers across a geodetic network, that identical angular error swing your final position wide by several decimeters. Because these errors in latitude and departure are constantly interacting with one another based on the bearing, they do not create a simple square box of uncertainty around our surveyed point. Instead, when we map out the joint probability of these errors three-dimensionally, they form an elliptical region of uncertainty known in geodetic surveying as the error ellipse. The orientation and shape of this ellipse change depending on our geometry, providing a visual and statistical report on the structural strength of our survey setup. Analyzing these error ellipses is a fundamental task in high-precision geodetic networks and modern GNSS baseline processing. The long axis of the ellipse shows us the direction of maximum weakness, where our survey is most vulnerable to errors, while the short axis shows our direction of maximum strength and precision. By studying these ellipses, we can identify weak links in our control networks, allowing us to strategically plan additional crossties or angular observations to round out the ellipse and ensure uniform, ironclad precision across the entire project. That's all for this chapter. Thank you.